In this lecture we talk about Chinese remainder theorem. So our first lemma is, we start with a ring A, and this ring say has two ideals A and B which are co-prime to each other. So they are relatively prime. So that means that A plus B will generate the entire ring A. So first result is that A intersection B is A times B in terms of ideals, and the canonical morphism, you go from A to A modulo this ideal A times A modulo this ideal B. This induces this isomorphism here between A modulo this product AB to A over A times A over B. So this is a canonical morphism, but this is an isomorphism. So this we want to show. So we have already seen in elementary group theory that for say n and m relatively prime integers, z over nmz, this is iso to z over nz times z over mz. So that is just a corollary of this lemma 1. So this just follows from here. So we can extend this result further in lemma 2. So say again you start with a ring. Now instead of just two ideals, you have a bunch of ideals. We are writing it as AI, where I goes from 1 to R. So there are R ideals. So there is a finite set of ideals of A, and these ideals are pairwise prime. So they're pairwise, say, co-prime to each other. That means AI plus AJ is A for I not equals to J. So A1 and A2, you write A1 plus A2 will generate A, A1 plus AR will generate A, A1 plus A3. So pick up any two ideals which are not equal, they will generate the entire ring A. So they are pairwise co-prime to each other. So then there is a canonical isomorphism. So same isomorphism here. Instead of two ideals, now you have R ideals here, and instead of two product here, you have this R products here. So just we are generalizing this right here. So this was this. Now we can further use the same result for modules. So say M is an A module, so A is a ring, and this ring again has these ideals AI which are pairwise co-prime. So everything in lemma 2 is holding in lemma 3. So then we have an isomorphism. Now instead of A here, we are writing M, and you modulo out this product and of these ideals in A times M here, and this goes to M over AI M. So this lemma 3 is easy to prove if we assume lemma 2. So first let us prove this lemma 3. So lemma 3, this is easy to prove if you assume lemma 2 holds. So we are saying there's a canonical isomorphism here. So there is an isomorphism here. You carry this entire isomorphism here, and then you tensor both sides with M. So this is precisely this. This thing is precisely this. And you tensor now both sides with M. So tensor M, tensor M. So tensor this side with M and tensor this side with M. That's precisely what we have done here. So this will also be an isomorphism. But this by definition, this thing by definition is this. And this thing by definition is this. So this thing is precisely this thing by definition. If you know tensor products, then you know this definition holds. And product again goes from 1 to R. So that is the number of these ideals A1, A2, A3 all the way to AR. So these ideals AI which are pairwise co-prime. So we know in general that this product of two ideals A and B, this lies within ideal A, and A and B also lies within ideal B. So you can see that AB lies within A intersection B because it lies in both A and B. So take an element X in A intersection B. Now we know that A and B are co-prime, so A plus B generates the entire ring A. So there are elements A and say B in this ideal A and ideal B such that A plus B is 1. Only then we will be able to generate the entire ring A. So therefore, so you set X as AX plus XB. So this is a sum of two elements of AB. Obviously because X lies in A intersection B, so AX plus XB will lie in AB. So therefore x lies in AB. So this x lies in AB because this lies in AB and this lies in AB. So therefore now you have A intersection B lies within AB. So we started with an element x in A intersection B, and we showed that this element x lies within A times B, and therefore A intersection B lies within AB. So therefore AB is equal to A intersection B. So this part we have now shown. So first thing, notice that this intersection of this ideals A and B, this is the kernel of our phi. So this is the kernel of phi, precisely because this lies within both A and in B. And you can also see that this A intersection B is precisely AB. So this map phi is therefore constant on each residue class modulo AB. So we have this mapping theta from A modulo A times B to A modulo A times A modulo B, and this mapping is kind of natural. I mean, whatever we have said here is very natural, because you can just simply see this mapping as mapping here. So you say take E, an element of ring A modulo AB, it maps to E modulo A times E modulo B. And anyway, in case of doubt, you can always rework out this example in terms of this map here. Pick n as 2 and m as 3, and then you can see this z over 6z, what will be the natural map to z over 2z times z over 3z. So 2 and 3 are relatively prime. So this is our natural map, and now you can see this thing also clearly. So this is almost kind of trivial. So this is obviously a homomorphism, because this modulo map, these two modulo maps are obviously homomorphisms, and we do all operations coordinate wise. So we do all operations coordinate wise. And this taking modulo out by an ideal, this is a standard homomorphism. So since var phi inverse of 0 is AB, because A intersection B is AB, and theta inverse of 0 is just 0, theta is injective. So it remains to show that theta is surjective. So injectivity is clear, because inverse of 0 for theta is just 0. That is precisely because var phi inverse of 0 is AB, which followed from A intersection B equals to AB, because this A intersection B was the kernel of var phi. So in order to show that theta, or equivalently say var phi or phi, is surjective, we have to find any pair, say y in A and z in A. So we have to find some y here and z here, so that they come from some x here. So we have x plus A is y plus A, and x plus B is z plus B. So z is coming from here and y. So this relation corresponds to this, and this relationship corresponds to this. So for yz we need to find an x so as to prove it is surjective. So you take some A in A and B in B such that A plus B is 1. Again, this comes from this relationship here, and we have talked about it right here. And you set x as az plus by, and that is the only thing we need to worry about. So this is the central piece of surjectivity. So then you modulo out with A, so x is equal to by. So we are modulo outing by this ideal A, so you just get by, first thing becomes 0. But instead of by, now you can write b is equal to 1 minus a. So you write 1 minus ay. So you can again write it as 1 minus ay. Again, since we are modulo outing by a, this term goes away, so you just left with y. So x is equivalent to y modulo a. So you have this thing which holds. Similarly, we can do the same thing for x equals to modulo b. You can start by modulo outing b here. This becomes 0, 0. Then instead of a, you write 1 minus b, and do the same procedure. You get x equals equivalent to z modulo b. So we have been able to prove injectivity, which was easy because a intersection b was ab, and var phi inverse of 0 was ab. So theta inverse of 0 was just 0, and we have to we have been able to prove surjectivity by just this relationship which came from here. So we proceed by induction. So lemma 1 was the case when r was 2, and we proceed by induction on r. So we will construct a new ideal B, which is just product of A2 all the way to AR, and we will show that A1 plus this new ideal B, this generates the entire ring A. So these two are co-prime to each other, or relatively prime to each other. So then we can use induction to complete the result. So for I greater or equal to 2, we have A1 with AI is A, because all these ideals are relatively prime. So you pick any two of them and you sum them up like this, they will generate the entire ring A. So therefore there are elements like Ci say in A1 and AI in this ideal AI, so that you sum them up, you get 1. So corresponding to every AI here, you can pick some element here in this ideal so that their sum is 1. So now you take product from 2 to R. So obviously because I is greater or equal to 2, so you go from 2 to R. So you take the product. So every factor will have Ci in it except the last factor, which will say have A2 all the way to AN. So you can think of this in terms of taking the product in binomial theorem. So there is only one term which will have all these terms A2, A3 all the way to AN. Now this C will come, this C is the rest of the terms in this product. So C is sum of the terms, each of which contains at least one Ci as a factor. So this is the only term which will not have no Ci's. Every other term which we have combined here in C will have some Ci. So if it has some Ci, then this in Ci belongs to this A1, therefore this C will belong to this ideal here. And this, so this belongs to our ideal A1, and this belongs to our ideal B, as we have seen here. So it follows that this A1 plus B generates A, because this A1 is here, B is here, and 1 is here. So they have generated 1, and therefore they generate the entire ring A. Now this, so therefore they are relatively prime to each other. Now you can use lemma 1 and same theorem. So instead of A, we have A1, so you have this thing. And now according to induction hypothesis, we said we are using induction. A over B was from A2 to AR, so which is isomorphic to this by our induction hypothesis. So we have gone 1 up. So if you count this is R minus 1 terms, so R minus 1 ideals. From here we have gone to these R ideals. So the lemma follows by composing these two isomorphisms, this isomorphism and this induction hypothesis isomorphism.